All right, there we go. Well, it looks like I'm lagging a little bit, so I'll give it a second to try and catch up, I guess. Let's see what the chat says. Yeah. Well, it's not even showing up there, is it? No, if I, oh, okay, there we go. Weird. All right, back on track. Sorry, everybody. Okay, so, okay, sorry, can everybody at home on the Zoom call now see those notes? Hopefully, yes. I'm going to assume yes until someone, okay, cool. All right, sorry, back on track. So that's how we would evaluate that numerically. A chart. I'm going to show you in a second a case where that it gives you very misleading results, okay? But we could have also evaluated this limit. This is a graph that I made of this function right here, x times the square root of 1 plus x. If you plot it, this is what you get. And so remember, when you're looking at a graph, you don't really have to do it with this graph, but you might as well, when you're looking at the limit as x approaches 3, you might as well cover up what actually happens at 3. Because if you're lucky, what's happening at 3 is really what's happening with the limit. But if you're not lucky, it's just going to influence your answer in a bad way. Okay, so if I cover up what's actually happening at 3, well, this side of the graph, it looks like I'm approaching between 5 and 7.5. That looks like it's about 6, right? Where the black line is covering up the graph. And same way here, it looks like we're approaching 6 from the right. And so we would also say from this that the limit as x approaches 3 of x times the square root of 1 plus x, this is equal to 6. And this hints at something we're going to see over the semester where the limit actually is the value of the function. That's a special type of function that we call a continuous function. You don't have to remember that right now, but continuous functions essentially are functions that you can draw without having to lift your pencil up. That's a very informal definition, but it's also you'll very rarely go wrong with that definition of continuity. Okay. So any questions on finding limits by a graph or by a chart of numbers? So I got a question that said, someone asked what I mean by covering up 3. I again just mean take on notability or whatever you're doing this, if you have a graph, just draw a straight line over x equals 3 to cover up, to hide what's actually happening at 3 so that you can look at just the limit from the left and right. Okay. And then you can erase it when you're done. All right, so limits that fail to exist. We looked at a lot of limits that we were able to calculate, but there is a lot of times where you can't calculate a limit because it fails to exist. So the first way that we saw was when we had something that looks like this. This is called the Heaviside function. Oh, that looks so bad. Let me move that up a little. Well, I guess that doesn't line up with the grid on notability, so say lovely. All right. So this is supposed to look like a straight line at roughly y equals -2 and a straight line at y equals +2 from the left and right. And so if I'm looking at the limit as x approaches 0, you can actually write this function down in one easy way as 2 times the absolute value of x over x. Well, if I look at what's happening from the left, first of all, cover up what's actually happening at 0. because again, it's only going to influence your answer in a negative way. Okay, so if I cover up what's happening at 0 and I look at what's happening as x approaches 0 from the left, well, I mean, again, I drew it a little bad, but it looks like it's y equals -2, right? So as x approaches 0 from the left, we have the limit looks like it's -2. But as we approach from the right, the limit is +2. And so the function itself never settles down to one value as we approach 0. And so this limit does not exist. Oops. This limit does not exist. D and E. Are there any questions about that? Why that limit doesn't exist? This limit would still not exist if I even defined the value there to be one thing or another. What really tricks people is when you have it something like this, and then you define the function to be 0 at 0. And then the reason that tricks people is because they think, well, if it's approaching +2 from the right and -2 from the left, then if I just take their average, then that could be the limit. But no, again, you cover up what actually happens at 0. We don't care about the function definition at 0. We only care about what's happening close to the point, not at the point. Okay, so that's why that line of thinking doesn't hold up when it comes to limits. Moving on, another way a limit failed to exist was if the limit blew up, right? If we had, if we were looking at something like limit as x goes to 1 of 1 over x minus 1. Well, this function, if I draw it, and you guys will learn how to draw functions like this, like in a pretty precise way, just from a few bits of information. But if you draw it, we're going to get something like when I plug in 2, I get 1. So this goes like that, and then I get something like that on the right. And then when I plug in 0, I get -1. You're going to get something like this on the left, right? So here's an example where, again, yeah, we're not approaching the same infinity, quote unquote, from both sides. But even still, if the function's blowing up, it's not settling down to one number because infinity is not a number. If you wanted, you could say the limit as x approaches 1, let me zoom in, the limit as x approaches 1 from the right of 1 over x minus 1. You could say that that equals, I'm going to put this in quotes, positive infinity. But also just saying that the limit doesn't exist is fine with me. Okay. In the same way, the limit from the left, you could say is equal to negative infinity. That again is just a way of saying that the limit doesn't exist, but you're sort of saying how it doesn't exist. It's blowing up. So you're giving a little bit more information with that answer. So that's why some people prefer to give that answer. All right, there's one more way in which a limit fails to exist. And it still relies on the fact that this function that I'm about to draw here doesn't ever settle down to one number. So we're going to look at the function y equals, well, we're going to look at the limit as x approaches 0 of sine of pi over x. Okay, so this function, as x gets very, very big, then sine of pi over x, well, pi over x is getting very, very close to 0, so it's looking like sine of 0. So this function does something like this. It's always bouncing, I'm going to zoom in a little bit. It always bounces between, this is +1 and this is -1 here. So it always bounces between plus and minus 1. So it does something like, this is a very inaccurate sketch, just so everybody knows. But as you get closer and closer to 0, it keeps bouncing back and forth, back and forth, back and forth between plus and minus 1. Okay? At 0, it doesn't matter how we define f to be, but if you want, you could say sine of, or you could say that we define this to be 0 at 0. It doesn't really matter. But if I want to look at this limit, who has a guess as to what's happening here? What my answer would be, the limit as x approaches 0 for this thing. Anybody? Is there any one number that it looks like this function is settling down to? No, it keeps bouncing back and forth between plus and minus 1. And so again, if you just drew the solid black line over x equals 0, I mean, that helps a little bit. In this case, it doesn't really help because as you approach 0 from the right, again, this function never settles down to one number. Okay? So that's the third way that a limit can fail to exist. You can have these wild oscillations as you approach a number between two fixed things. Now, it's okay for a function to be very oscillatory like this, and by oscillatory, I just mean very wavy as you approach something, as long as the waves are what's called decaying, as long as they're decreasing to some number. But here, again, we have something that keeps bouncing back and forth between plus and minus 1. So the idea is, no matter how close to 0 I am, I can find an x value where sine of pi over x is positive 1, no matter how close to x or how close to 0 you are. And you can also find an x value where sine of pi over x is negative 1, no matter how close to x you are. So that tells me that the limit, you're sort of in theory getting two different limits there. Okay? Are there any questions about this? This one's a little weird, I understand. But it will come up because it's an important example of why limits, when limits don't exist. Okay, this is one that I would suggest plotting in Desmos, your Desmos app once you download it, because they can give a slightly more accurate graph than this sketch. All right, so on this example, let's say you had just tried to evaluate this numerically. Well, if you plug in negative 1/10 into sine of pi over x, well, if I plug in 1/10 into 1 over x, 1 over 1/10 is just 10, right? So this value here, sine of pi over negative 0.1, that's the same thing as sine of negative 10 times pi, right? Because again, 1 over 0.1 is just 10. So that's all the simplification I did there. Does anyone know what the sine of negative 10 pi is? Okay, if you don't. In general, if you have sine of any integer times pi, pi is always a half, 1 pi is a half rotation around the unit circle. And so 1 pi, sine of 1 pi is 0. Sine of 2 pi is, you go the other half. Sine of 2 pi is 0. Sine of 3 pi is 0. Sine of 4 pi is 0. Sine of 5. So sine of any integer times pi is 0. Okay? This is 0. All right. So what about sine of pi over negative 0.01 or negative 100? Well, that's just sine of, I'm dividing by 100, so I'm going to get sine of negative 100 pi, right? And what is that value? That's sine of some integer times pi. So that is 0. I heard it. And what do we think the next value is going to give us? 0, that's right. And the same way over here, I'm going to get zeros for all of these. So if you just looked at these x values, it looks a lot like this limit here would give you 0. But it's not, because if you had picked these a little different, you could have gotten 1s in this chart. You could have gotten negative 1s in this chart. You could have gotten really anything that you wanted between -1 and 1. And that's sort of the key property of these functions that oscillate wildly between two fixed numbers, is you can get, when you're filling out a chart like this, you can make the limit look like anything you want, and therefore the limit doesn't exist at all, okay? So if you want to see an example where this chart gets you all 1s, just ask me later and I'll fill out a chart with the proper x values to show you that. All right, so the takeaway is that numerically evaluating limits can trick you into thinking that a function has a limit as x approaches a when it really doesn't, okay? That's the key takeaway from that last example. Admittedly, that example is a little bit contrived, and you wouldn't really see that in the wild. But you do need to know that if on an exam I'm trying to trick you, you need to be able to spot the trick, right? So know that wildly oscillating functions don't really have limits when in that sense, okay? So the big idea behind all these examples is that the function f of x never settles down to one value as x approaches what's called the limit point. I'm not ever going to say that. As x approaches what we're calling a. Either because it has different limits from the left and right, and so therefore if f is approaching one thing from the left and a different thing from the right, it can't be approaching a single thing from both directions, right? Or it blows up, or it oscillates wildly between two fixed values. Now, here's an example that looks similar to the last one I just gave, but this one I'm trying to trick you into thinking that this limit doesn't exist. This limit does exist. So find the limit as x approaches 0 of x times sine of 1 over x. Well, I know sine of 1 over x oscillates between plus and minus 1. X, what happens to x as x goes to 0? It sounds like a trick question almost. As x goes to 0, what happens to x? Yeah, it goes to 0, right? Like by just words. So that as x goes to 0, x goes to 0. So here you would, to draw this graph, one way that you could draw this graph, there's that, there's that, there's that. This is another graph that I highly suggest plotting in Desmos because they can give you a much better sketch of this. But this sketch isn't going to be too bad. This function, instead of oscillating between plus and minus 1, because I'm multiplying this by this x here, this will oscillate between these two lines here, plus or minus x, okay? And so this function is going to look something like, again, this is a sketch. It's still going to oscillate wildly, but it's going to shrink down to 0 like that as we get closer to 0. So this is an example where you have wild oscillations, but you still have a limit as x approaches 0, something like that. There we go. Okay, and so what is the limit as x approaches 0? Yeah, it's just 0, right? If you zoom in, cover up x equals 0, this function is getting closer and closer and closer to y equals 0. Does that make sense to everybody? Because that x factor is shrinking everything into the origin. The x factor. Any questions on this example? So the key takeaway here is wild oscillations on their own don't guarantee that a function doesn't exist if something else is shrinking those oscillations down. All right. So here is that function zoomed in a little bit. So now we're just between plus and minus 1. And you can see that I didn't trick you. This is really what's happening. There's the dashed lines that I drew before. This function is staying between those dashed lines. So that's what happens with sine of 1 over x times x as x approaches 0. Any questions? All right, so let's find the limit graphically by plotting a graph of this function. So I want to find the limit as x approaches -2 of 2x squared plus 7x plus 6 over x plus 2 by using a graph. How do you want to graph this? First of all, it looks like maybe there could be a blow up because if I plug in -2 in the denominator, I get a 0, right? But thankfully, if I plug in -2 in the top, I'm going to get, I should also get 0 the way I constructed this. Do I? Did I mess everything up? Minus 14. 4. No, I think you get 0. So when you plug in 0 into the top and the bottom, you should get, or sorry, when you plug in -2 into the top and the bottom, you get 0 in both places. So maybe that cancellation is going to give us a finite limit. We don't know. There's no way to know until we start plotting the graph. So we can't plot what's happening at x equals -2. Eventually, I'm just going to cover that up because, again, when you're finding limits graphically, just cover up the x value you care about. So, well, what about x equals -1? What's the function value there? Well, I'm going to get 2 times -1 squared plus 7 times -1, so -7, and then plus 6, right? That gives me 2 minus 7 plus 6, which gives me what? 8 minus 7 is 1. So at -1, I get +1. Okay, what about 0? 0 is always a nice thing to plug in. When I plug in 0, I'm going to get 2 times 0 plus 7 times 0 plus 6 over 0 plus 2. So at 0, I get what? 3. Excellent. 1, 2, 3. All right. That was probably really loud for Zoom people. I'm sorry. And then let's plug in 1. What do we get when we plug in 1? 5, perfect. 15 over 3, right? 2 times 1 plus 7 times 1, that's 9, plus 6, 15 over 1 plus 2 is 3, so 15 over 3 is 5. So 5. Huh, that's funny. It looks like like this, to get from this one to that one, it's not funny, I planned this. To get to this one from that one, I went up 1, or sorry, up 2 over 1. This, to get from this one, from this one, I went up 2 over 1. That's looking like a straight line. Could this thing just be a straight line in disguise? It is. So I planned this way. This is just a straight line in disguise. So it looks something like no, that's a little bit off. It's going to look something like this. It's got a slope of 2. Again, we've got a hole in the graph at -2. This function is not defined at x equals -2 because I can't divide by 0. But that doesn't matter when it comes to the limit. Okay? Because let's just cover this up. Give me a straight line. Okay, whatever. So when I cover that up, I mean, what does it look like this function is approaching? Is that line a little too thick? Yeah, exactly. And that's exactly the right answer, the -1. Okay, so this limit here is the limit as x approaches -2 of 2x squared plus 7x plus 6 over x plus 2. This is equal to -1. All right, so how can you show for yourself that that is actually a straight line, with the exception of that hole in the graph? Who has a guess? Well, yeah, what was it? How can I show that this function here, well, when we plotted it, we got a straight line. It doesn't look like a straight line, right? So yeah, perfect, perfect. Yeah, we do. All you have to do is factor the top. If you factor the top, then you're going to get x plus 2 times 2x plus 3, if I remember right. And then divided by x plus 2. That's what the top looks like. And this is a hint of what we're going to be looking at next week. This is how we're going to be evaluating our limits next week. So then I cancel x plus 2 from the x plus 2. I end up with 2x plus 3, which is exactly what this line looks like that I plotted here, right? That's what that line is, 2x plus 3. So that's a computation that you're going to be doing a lot next week. Most of calculus relies on computations like this. As far as when we start talking about what the derivative is, you're going to be doing this type of calculation almost constantly for at least a day. Okay, are there any questions about this? Why was I able, if you evaluate this using this method, I canceled x plus 2, right? You can't cancel x plus 2 when x is -2 though, because that gives you 0, and that's where we're looking at, right? X equals -2. So why would I be able to cancel that? You can give me an answer. Because in general, you can't cancel 0 over 0. You can't cancel that out. But in this case, we're looking at the limit. Remember that. And when we're looking at the limit, I'm not actually looking, I don't actually care what happens at x equals -2. So I'm ignoring essentially x equals -2, which means I can cancel x plus 2 from the top and bottom. But we'll get into that more next week. Okay. All right, so find the following limits if they exist. This is going to be very similar to a homework problem you're going to have. So I'm going to draw this graph in. The limit as x approaches -2 of f of x. So this graph is going to look something like this. And then at 1, we're doing something like this. And then at 3, we're doing something like this. So here's this weird function. It is a function. It passes the vertical line test, right? If you draw a vertical line anywhere, the only places that maybe it wouldn't pass the vertical line test are maybe at 1, but it's only defined to be this at 1. So if I draw a vertical line through x equals 1, it only intersects the graph once. Same way at 3, it only intersects the graph once, right there. And at -3, that clearly passes the vertical line test because the function is not even defined at x equals -3. Okay, so we want to find these limits. All right, let's start with the first one. What is the limit as x approaches -2 of f of x? By the way, the blue stuff is f of x. Okay, well, we want limit as x approaches -2 of f of x. Well, who can tell me? We've seen a limit like this before. It does not exist. From the left, we're approaching positive infinity. F of x is approaching positive infinity. From the right, f of x is approaching negative infinity as x approaches -2. So this limit does not exist. Okay, what about the limit as x approaches 1 of f of x? Well, that's that part of the graph there. Does not exist also, correct. Because if I cover up what's actually happening, well, from the left, I'm approaching, it looks like 0. From the right, it looks like I'm approaching 2. Because those two aren't the same number, f of x is not settling down to one thing. And so the limit here also does not exist. Okay, what about at x equals 3, the limit as x approaches 3 of f of x? Excellent, 4. Yes, it is not negative 4, where what the function is actually defined as. That is just there to trick you. It is positive 4 because, again, cover up what's actually happening at x equals 3. So if we look at this, let me draw in another line. There we go. If we look at this as x approaches positive 3, I mean, now it's obvious, right? Now it's obvious, like, because we're ignoring that point at the bottom, it's obvious that f is approaching positive 4, right? So the limit as x approaches 3 of f of x is equal to positive 4. Any questions on that in this example? You're definitely gonna have a homework problem like this next week, just so you guys know. Oh, I got chats. Oh, excellent. Thank you, everybody, for participating. Okay, so if we've got no questions, then we're going to be moving on to, we're going to get in today a little bit into the formal definition of a limit, okay? So now that we've got a little bit of intuition for what limits actually are, before we start talking about what I said before about canceling out that factor of x plus 2 and evaluating limits analytically, we need to look at the definition, the formal definition of a limit. So remember that I gave you an informal definition that said that the limit as x approaches a of f of x is equal to L. That means that if I make x really, really close to, but not equal to a, then f of x has to be really, really close to L. Okay. And we saw examples where f of x could just equal L the whole time, right? Constant functions. So that's why I don't have f of x is really, really close to, but not equal to L, because that would actually throw out some examples where it would make sense to say the limit exists. Okay. All right. So how can we make this idea of closeness? How can we make it make mathematical sense? And there's actually multiple answers. Most of them are very abstract. And anybody who wants to be a math major, you'll see other ideas of how you can define closeness. Okay, so plug for the math major. So, but the definition that we always use in Calc 1 is we're going to call epsilon, for historical reasons, we always use epsilon. So epsilon is a very, very small but arbitrary number, okay? So this weird e here, that is epsilon, okay? So epsilon is some small but arbitrary positive number. So the idea is like if I come in here and I say epsilon equals 0.001, then you would say f of x is really, really close to L means that the absolute value of f of x minus L is less than epsilon. Okay, so in other words, if we're looking at a graph, let me move on a little bit. I'm coming back to this, I promise. If we're looking at a graph and here's some L. Then here's L plus epsilon, and here's L minus epsilon. Then f of x minus L is less than epsilon is all of this stuff in between here, all those numbers in between there, okay? So that's what that means. F of x minus L is close to, f of x is close to L means the absolute value of f of x minus L is less than epsilon, okay? So are there any questions? Sorry, I should have put that slide right after. Are there any questions about why this is what we mean by f of x is close to L? Okay. So then I also in that definition said that x has to be really close to A, but not equal to A. But it doesn't have to, x doesn't have to be really close to A in the same way that f of x is really close to L. So for that reason, we're going to say we have another small positive number, delta. Okay, but it serves the same purpose. It serves the same purpose to say that if delta is very small, then the absolute value of x minus A is less than delta. That just means that x is very close to A. How close? Well, it's within delta units away, but not equal to. That's why we have this 0 here. That 0 keeps x from equaling A, because if x equals A, we actually do get 0 there, right? So that's why we have 0 is strictly less than the absolute value of x minus A, and that's less than delta. Okay. So this guy says f of x minus L and absolute value is less than epsilon. That tells me that f of x is close to L. How close? It's within epsilon units vertically. This tells me that x is close to A. How close? It's within delta units. Okay? So this is what we mean by closeness. So keep that in mind when we look at the formal definition of a limit. All right, so here's the formal definition. The limit as x approaches A of f of x equals L. This means that if I walk in and I give you an epsilon, a very small number, then you can work out a delta, another very small number, such that if x minus A is less than delta, which that means that x is close to but not equal to A. So again, that's why this 0 is here. Then f of x minus L in absolute value is less than epsilon. Okay, so the way the formal definition works is always you're given an epsilon, and then you have to find delta, so that if x is within delta units away from A, then f of x is within epsilon units of L. Okay. So that's the formal definition. Yes, f of x minus L could be 0. You're allowed to have f of x be L. Okay, that's actually the very first limit that I'm going to prove rigorously with this formal definition is the limit of a constant function is just the constant. Okay. All right, so now that we have all of that, here's the idea. I walk in and I say epsilon equals 0.01. How close does x have to be to for f of x to be within 0.01 units of it's actually 8 here, the way I drew it. All right, so the limit, again, the limit here, this is 8, but I'm just going to write L to keep things general. I come in, I say epsilon 0.01. So let me zoom in a little bit. So here's L plus 0.01. Here's L minus 0.01. Okay, so we want to know, let me change colors here, because this is the bound that we want. We want to know how close does X have to be to A so that f of X stays within those two red lines. Well, looking at this, f of X is between those two red lines, just between whatever X value gives me that and whatever X value gives me that, right? Does that make sense? If X is no more, or X is no less than this, if I drop this down to the X-axis, and X is no more than this guy, then we're going to stay between those two red bars there on this line. We're going to stay between there and there, which is where we need to stay for this formal definition. Okay, so graphically, in my mind, graphically, it's actually easier to see what delta needs to be. Delta just needs to be the smaller, if I zoom in here, delta just needs to be like, here's, oops, let me get a smaller. Here is some number, here's some width. They look roughly the same. One of them is actually bigger though. So this one we'll call delta 1. This one we'll call delta 2. So as long as we stay within the smaller of these two intervals, we're going to stay within epsilon units up here. Okay, and so actually delta 1 is the smaller one because this one's a little bigger. So you would take delta equal, in this case, delta equal to delta 1 to make sure that we are staying between these two red lines up here on the graph. Okay, so lots of zooming with these, lots of zooming in on the graph. Are there any questions? I'm going to show how to use this definition to formally calculate limit. I'm never going to have you guys do anything more than a straight line with this, okay? Because it is, I do recognize it's a little technical, but I think you can do it with straight lines after you've seen some computations of some examples of how these calculations are going to go. Okay. Are there any questions for me? That was my hands, everybody at home. Are there any questions for me about limits? Good question. Yeah, the epsilons up here are the same. The delta is what you have control over. Epsilon you have no control over. I walk into the room and I say make f of x within 0.001 units of L. And then you say, okay, here's what delta needs to be. So you are picking delta carefully so that you stay within that range. But the epsilons up here are both the same thing. Epsilon is plus 0.01 and minus 0.01, but excellent question. Yeah, any other questions about this? Okay, and then the next one, you don't have to do this as homework or anything, but just so you know, next class, we're going to be looking at a calculation like this, the formal definition of a limit to prove that the limit as x approaches 1 of negative 2x plus 4 is positive 2. Okay. All right, if you guys don't have any questions, feel free to go. Remember, my office hours are today from 1 to 3. people meeting in person, leave your name tag where it is, and please wipe off your desk before you go.